let's talk about the analysis of area functions. And to get into the spirit of this, I would like to define f of t by a graph. And so here comes my f of t. And just to make this reasonable, make this scale -5 to 5. And likewise here. And this is going to be our t-axis. This is going to be our f of t-axis. And now what I'm going to do is to define f in terms of a couple of simple shapes. Let's get that a little bit. Sometimes when you draw lines, it can hard to get the right slopes on it, but I think we're good now. Okay? So this is going to be our f of t. And now we're going to let g of x be equal to the integral from 0 to x of f of t dt. You know what? I'm actually going to change my starting point here so that it can be a little bit clearer. I'm going to start integrating at negative. Now, starting at negative, starting at -1. There we go. And now our goal is going to be to graph g of x. To graph g of x. And our plan for achieving that goal is going to be to use our calculus tools. And the reason we have to use our calculus tools is that g of f is a kind of function that we just have not had a lot of experience with. It is in the family of functions of area functions. And we don't know a whole lot about area functions. And so because of that, we are not going to be able to just like look at this graph and say, oh, g of x has the shape of blah, 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 blah. Instead, we're going to need to analyze using the calculus tools that we have. In particular, our plan is we're going to find a reference value. And that reference value is going to be the value at the starting point. G of -1 is automatically equal to what value? No, be careful. What is g defined as? G of -1 is the integral from -1 to -1 f of t dt, which is 0. That's right. So Mark just fell into the first trap students will often fall into. I'll ask them about g, and they'll tell me about f. Don't do that. Make sure that you're answering questions about g. So our first plan is we're going to find the reference value, g of -1 is 0. Second of all, we're going to use g prime to find local extrema and increasing and decreasing behavior. And then third, and usually optionally, we're going to use g double prime to find concavity and points of inflection. Concavity and points of inflection. But this is often not necessary because usually the local extrema and increasing, decreasing behavior is enough to get a pretty decent section.
So number 3 is optional.
So number 3 is optional unless you really need to. So that's our plan. And to execute our plan, I want to remind you of what we talked about yesterday in class, which is the relationship between G and G prime. Tomorrow, I'm going to develop this in a formal theorem called the fundamental theorem of calculus. But for today, I'm going to consider what does it mean to ask about the rate of change of G. G adds up all of the area from -1 to x, all of the net signed area from -1 to x of this curve right here. So G prime is going to be the rate at which that area changes. So to get at that rate at which the area changes, what I'm going to do is to let x change by a little bit, dx. Just a little bit. And when I do, I get a little bit of extra area added on right here. And that little bit of extra area is approximately a rectangle. And it is the extra area that we are adding on, so we're going to call that dA, the differential amount of area that is being added on. And because this shape is approximately a rectangle, we can say that dA is equal to the height of the curve at point x times the width dx. So here is our basic equation. Area equals height times width. And if I now divide both sides by dx, what I find is that the rate at which the area is changing, which is dA dx, is in fact equal to f of x. Now I cheated a little bit here when I went from here to here, because the derivative, which is spelled dA dx, is the limit of a difference quotient, whereas here I made it the quotient of two little tiny quantities. So that was cheating. It's really approximate. But, as we're going to see tomorrow, in fact, this is an exactly correct relationship. And so this led to our slogan yesterday. The slogan is that the rate at which the area changes is the height of the curve. The rate at which the area changes is the height of the curve. The rate at which the area changes is the height of the curve. Okay. So now with all of that in mind, I'm going to take all of that and shrink it down. Tuck that right up there so you can remember it. And with all of that in mind, we're now ready to find all of these things right here. First of all, we find our reference value. And our reference value is always found at the starting point, and the reference value is always 0. Because if I integrate from -1 to -1, I will get 0 width. And there it is. So that tells me one thing about G. I know that G of -1 is 0. Yes?
So, reference value always has to be 0.
The reference value, well, we can compute as many reference values as we want, but the easiest one to pick is the initial or starting point. So if I do, then I get 0 every time. Right? Yep. I could have also chosen x equals 0, or x equals 1, or x equals whatever, and then I would have had to actually find some area. This was easy. The next thing is I'm going to use G prime to find local extrema and increasing and decreasing behavior. And so I start with the fact that G prime of x is f of x. G prime of x is f of x. And so what that means is that I am actually looking now at a graph of G prime. Because I'm looking at a graph of f. And so I can now do a well-labeled number line for G prime by using the number line for f. Now here's where students will get confused. When I find the number line for G prime, which is f, I'm not going to look at the slope of f. I'm going to look at the actual values of f. F is 0 right here at x equals negative 2.5. And for x is less than that, f is negative. And for x greater than that, f is positive. All the way out until x equals 3, at which point f goes below the axis again. So that I now have a sufficient amount of information to find local extrema and also to find increasing and decreasing behavior. Where are the local extrema of G? G has local min at x equals negative 2.5. Why?
Because
it's interesting that you said F. You could have also said what? G prime, right. That would have made sense, right. Exactly. Which one should I say? That's a really interesting question. G prime connects this to G, but if I say F, that connects it to the evidence before my eyes. So you know what I actually do? I actually say both. I say because G prime, which is equal to F, changes signs right there. And so what that does is it connects to what I'm talking about, and it also connects to the evidence I see before me. That's a simple and easy way to have a really nice, complete answer. Any other local extrema? Give me the whole thing.
G of x has a local max x equals 3, whereas G prime is equal to F equals signs positive.
Good. Good. I can also observe where G is increasing and decreasing. I can observe that G is decreasing from negative 5 to negative 2.5. Because G prime is less than 0. Oh, there was another interval too, wasn't there? 3 to 5, I think. And I can observe that G is increasing on the interval negative 2.5 to 3 because G prime, which is F, is constant. Now, again, I cannot emphasize this enough. To get these results correctly, you really, really have to appeal to the sign of G prime theorem. Because if you try to just look at the graph, you're going to get it wrong. Because F is increasing from negative 5 to 0, and it's decreasing from 2 to 5. And a whole lot of students will be tempted to take the increasing and decreasing behavior of F and apply that to G. This is not a graph of G. This is a graph of G prime. So in order to get this right here, you have to use the theorem and recognize that we're looking for where G prime, which is F, is less than 0. Does that make sense? Okay. Now, armed with all of this, we are just about ready to do a graph of G, but we can actually do one more thing. Do you guys remember we did this kind of stuff before, and we sketched graphs and stuff? But we can actually do one more thing that we could not do before. We can actually find values, y values, at x equals 3 and x equals negative 2.5 by doing inverse. So let's find those values. Let's find the value of our local min at x equals negative 2.5 by evaluating g of negative 2.5, which is the integral from negative 1 back to negative 2.5 of f of t dt. And to get that integral, I need to go back to my graph right here and do some net signed area. From negative 1 back to negative 2.5, that shape is a triangle, and it has a height that looks like 1, and has a width of 1.5. And so this net signed area is going to be a half of 1 times 1.5, which is going to be 0.75. And I see that hand, because I'm integrating from negative 1 back to negative 2.5, I need to first of all do a reversal so that I'm integrating proper direction. And now I can fill in the value of the net signed area. This gives me an actual y value for my local minimum. It is going to be at negative 3/4 or negative 0.75. And I can do the same thing for my local max. For my local max, I have an x value of 3, and so I can actually compute the value g of 3, integrating from negative 1 to 3 f of t dt. Come back to my graph, negative 1 out to 1, 2, 3, right here. I'm looking at all this net signed area, and I've got a special shape, a trapezoid, which has a base of 4, and has a base of 2, and has a height of 1.5. And so its area is going to be a half for the average of the bases times the height. Which is going to be equal to 4.5. So this gives me now a y value for my local max. So we have 1, 2, 3 points. We have our initial point, negative 1, 0. We have a local min. We have a local max. And that's enough for a sketch. Here we go. Negative 1, comma 0 is the initial point. The local min was at negative 2.5, negative 0.75. Negative 2, negative 3. So right here, there's our local min. And our local max is at 3, comma 4.5. 1, 2, 3, comma 4.5. Like so. And this is enough for me to say my graph is going to look something like this, like that. That's a pretty decent sketch. Now, does G double prime give us any additional information? Let's take a look at what G double prime has to tell us. First of all, it should be fairly clear that G double prime is equal to F prime. And so when I think about F prime now, in my original graph, I'm thinking about now the slope of F. So coming back to the slope of F, I can see that the slope of F is positive from negative 5 to 0. And right at 0, I can see that my graph of F has a sharp corner on it, which means that its derivative, F prime, which is G double prime, is undefined. And the same is true over here at x equals 2. So I can mark at x equals 0 and again at x equals 2, I can mark those with x's. And in between, my graph is horizontal, which means its slope is 0. So I'm going to have something that's kind of unusual. I'm going to have 0 instead of plus or minus for this thing. And then for x's beyond that, my slope is negative. Now what does that tell us about the graph of g? It tells us that g should be concave up until x equals 0. Negative 5 to 0. And when I look at my graph, I'm pretty satisfied that my g that I drew is concave up from negative 5 to 0. Yes.
So, we find G double prime because we can check it.
Yes, it allows us to check. If I've drawn my graph right from G prime, then G double prime will not add a whole lot to it, but it should be consistent with it. Also, G is concave down from 2 to 5. Oh, I forgot to put my because. Because G double prime, which is equal to F prime, is positive. Or another way to put it is because F is increasing. And concave down from 2 to 5 because G double prime, which is equal to F prime, is negative, or F is decreasing. And I should be able to check over here that my graph is concave down from 2 through 5. Now what happens between there? This is a very interesting result right here, where G double prime is equal to 0. That means my graph is not concave up, and it's not concave down. But it's not constant either. See, not constant. It's increasing. What kind of function has a 0 for its second derivative? It does not curve upwards and it does not curve downwards. Yes! A linear function has a 0 second derivative. Think of it. Y equals mx plus b, take a derivative, get m, take another derivative, get 0. So in between 0 and 2, we would say that g is concave neutral or linear. On the interval 0 to 2, because f prime is 0.
Can you just say it wasn't constant? Or like constant?
A constant function looks like this. A function with a constant slope can look like that.
So it does have a constant slope?
It has a constant slope. G has a constant slope, but it is not a constant function. Yes, sir.
So we figured out like on f of t graph.
Uh-huh.
0 and 2 are
Yes, what happens at 0 and 2? So 0 and 2 are going to be places where our function actually changes from concave up to concave down. That actually doesn't happen here. So we actually don't have, we probably would not classify these as points of inflection on the graph.
But we can say 0 and 2 is a point of inflection.
We would not
Oh,
say that they are points of inflection. I've never actually seen an AP question that has concave neutral functions involved with it, but this is how I would analyze it. This, the question you raised, Jason, about these guys, are they points of inflection or not, is really a question of definition. Would we say that the concavity did change from plus to 0, from up to 0, to neutral? Or would we say that the concavity did not change from concave up to concave down, so not be point of inflection? It all depends on how you're defining it. Yeah. So notice that in here, my graph should look like a straight line. All right, so let's go back through this whole analysis. It took us a while to do this, but once you're good at it, once you've practiced, it's not too hard. So what we did was, the main meat of what we did was to first find the reference value, easy. Second, we used g prime, which is f of x, to find the local extrema and the increasing and decreasing behavior. And the one thing that we added to that was that we could actually find y values, so that we actually have a good range of values here and here to come up between an x and n. That's pretty good. And then we just used a smoothish curve to get there, and then we could check ourselves with the g double prime integration. Does that make sense to everybody? That's our basic plan. Let's see if we can do a second one in 10 minutes, since we have about 10 minutes. Okay, so here's a good area function here. We're going to let g of x be the integral from 0 to x of sine t dt. And now we want to sketch g. That's our plan. Before we ever get to sketching g, let's go ahead and sketch f so we can see what we're talking about. And let's sketch g on a suitable interval. How about 0 to 2? Sounds reasonable. So here comes f of t, which is sine t. 2 pi, like so. And now we need a reference value. What's our reference value? At x equals what? Yep, it's actually x equals 0. The reference value is g of 0 is equal to 0. Remember that the variable of integration is a dummy variable. The real thing, the real variable here is the x. Okay, so that's our reference value. Now we're ready to use some information from g prime. And what is g prime of x equal to? Which is? Well, no, f of x is correct.
Okay. Which is the,
What is the f that we're talking about? Sine x. That's right. G prime of x is going to be equal to sine x. Notice that we are evaluating at point x specifically. Yep. Okay. I think now we're ready for a number line. What does my number line look like from 0 to 1 for g prime?
at pi, there is a change on
Where?
pi,
At pi. From what to what?
increasing pi plus to minus.
That's right. Plus to minus. Plus here and minus here. Exactly the same. Okay, good. And so based on this, we would say that g has
Local max at pi equals g prime equal to f of x
good. Okay. So we have a reference value. What is the value of that local max? What is g of pi? this, at this moment in time, you can use your calculator to evaluate this. So we go ahead and grab the calculator real fast. Y equals sine x integrate from 0 to pi and get a value which is 2. And so that tells me that I have a maximum value of 2 at x equals pi. I also, there were a couple of zeros that we left out, right? 0 and 2 pi at the endpoints. So just tell me I'm going to have horizontal tangents there. And so this is actually enough information for me to sketch a graph of G. I have a reference value of 0, so x equals 0. At pi, I'm going to go all the way up to 2. That's my local max. And then at 2 pi, I'm going to have a horizontal tangent again somewhere. Let me go ahead and find the value at 2 pi since it's at an endpoint. G of 2 pi would be the integral from 0 to 2 pi of sine of t dt. And guys, I don't need to work too hard. Yes, that's right. Tell me how.
Because under the same area and because the numbers is connected.
Awesome. Good job. So this is automatically 2 minus 2, which is going to be 0. And so I can tell that my curve is going to go up, like so, to the local max, and down like so, with a horizontal tangent at 2 pi and a horizontal tangent at 0. Yes?
So it can be like using symmetric.
Yes, it is. It is going to be symmetric. And in just about 5 minutes, we managed to knock out the graph of an area function. Let's use G double prime to confirm some stuff. G double prime is equal to cosine x. So if I do a well-labeled number line for G double prime, then I should have zeros at pi over 2 and 3 pi over 2. And cosine is positive, negative, positive, like so. So I should be concave up to pi over 2 with a point of inflection at pi over 2. And it looks like my graph is just about right. Concave up and then concave down. Maybe it needs to be a little better rounded. And then concave down to concave up at 3 pi over 2. My graph is basically correct. What does this look like, trig-wise? Does this look like any trig functions that you know?
Oh,
No, tangent doesn't look like that. It's got a vertical axis. Not sure? Okay. By the end of the week, you'll be able to answer that question. Yep.
So the reference point just gives us a point on the graph, right?
Yes, it gives us a starting point to mark our graph from. That's why we do it first, so we know where to go up or down from.
oh, we have like vertical.
No vertical tangents, no. There's a horizontal tangent. There are 3 of them.
Probably holding.
There's a horizontal tangent right here at pi, again at 0, and again at 2 pi. And those correspond to the zeros of our derivative. So good work.